Think about all the sounds you hear every single day. You know, a phone ringing, maybe a friend laughing, your favorite song on repeat. But have you ever really stopped to think about what sound is? We're always told it's a wave, but honestly, that just brings up even more questions. So in this explainer, we are going to dissect the very nature of a sound wave and uncover all of its secrets. And this, right here, is the central mystery we are going to solve today. It seems like a simple question, doesn't it? But trust me, the answer unlocks exactly how sound moves through the air to reach our ears. So let's think of ourselves as sound detectives, and our mission is to crack the case of the sound wave. Okay, let's dive in. So what's our game plan? First, we're going to investigate the two main types of waves. These are our main suspects. Then we'll dust for fingerprints, so to speak, and identify the four key characteristics that define every single sound wave out there. All right, let's jump right into part one, understanding the types of waves. And our key tool for this investigation, a slinky. Oh yeah, that classic toy is about to teach us some seriously cool science. Welcome to the slinky investigation. Okay, I want you to picture this with me. You've got a slinky, and it's stretched out on a long table. Got it? Your friend is holding one end completely still. Now you take your end, and you start pushing and pulling it, back and forth, back and forth. What do you think you'd see? What kind of pattern starts to form? You'd see this really cool wave moving down the slinky made of these bunched up parts and these spread out parts. Now, for your exams, you absolutely need to know these two keywords. The bunched up high density areas are called compressions, and those stretched out low density areas, we call those rarefactions. This whole pattern is a massive clue in our investigation. And what we've just created, well, that is our first suspect, the longitudinal wave. The really important thing to notice here is that the slinky coils are moving back and forth in the exact same direction that the wave is traveling. That's the key, folks. For a longitudinal wave, the particle vibration is parallel to the direction of the wave. You gotta lock that word in your brain, parallel. Okay, on to our next clue. Let's imagine that same slinky, but this time it's hanging from the ceiling. You give the bottom a little flick to the side. What happens? You see this hump travel all the way up, but the slinky itself doesn't actually go anywhere, right? It just moves side to side. So what's actually moving up? It's the energy. And this is a huge concept for all waves. Waves transfer energy, not matter. And this type of wave brings us to our second suspect, the transverse wave. Here, the particles of the slinky are moving up and down or side to side, which is perpendicular at a right angle to the direction the wave itself is traveling. So let's get this straight. Longitudinal is parallel and transverse is perpendicular. That's the main difference right there. Okay, let's put these two suspects side by side and really break it down. For a longitudinal wave, the particle vibration is parallel to the wave direction, and it causes a change in the density of the medium, you know, our compressions and rarefactions. For a transverse wave, the vibration is perpendicular, and it creates a change in the shape of the medium, like that hump on the slinky. So, what about sound? All right, the moment of truth. We've examined all the evidence. We've got our two main suspects, longitudinal and transverse waves. It's time to solve the mystery. What kind of wave is sound? And the verdict is sound waves are longitudinal waves. It makes perfect sense when you think about it. Imagine a speaker. When the speaker cone pushes forward, it squishes the air particles in front of it, creating a compression. When it pulls back, it creates a space, a rarefaction. It just keeps doing this over and over, pushing and pulling the air exactly like we did with the slinky on the table. That's what sound is. Okay, let's do a super quick recap of what we figured out so far. First, super important, waves transfer energy, not matter. Second, longitudinal waves have parallel vibration, while transverse waves have perpendicular vibration. And the absolute biggest takeaway, the one you need to highlight and star in your notes, sound in the air is a longitudinal wave. Case closed. Awesome, so we've identified our wave, we've solved that mystery. Now it's time to profile it, to look at its fingerprints. These are the four key characteristics that describe every single sound wave and make each one unique. Okay, so here's the thing. Drawing a bunch of squished and stretched out air particles every time is, well, it's messy and kind of difficult. So scientists use this clever graph to represent a sound wave. Now be careful. It looks like a transverse wave, but it's not showing shape. This graph shows the changes in air density. The highest points, the peaks, which we call crests, represent the areas of maximum compression. And the lowest points, the valleys, or troughs, represent the areas of maximum rarefaction. First up, we have our first fingerprint, wavelength. We represent it with the Greek letter lambda. It's really simple. It's just the distance from one crest to the very next crest, or from one trough to the very next trough. Basically, it's the physical length of one complete wave cycle before the pattern starts all over again. Fingerprint number 2 is amplitude. On our graph, this is just how high the crest is or how low the trough is from that middle line. Amplitude tells us about the wave's intensity. And for sound, this is super direct. A higher amplitude means a louder sound. A lower amplitude means a quieter sound. It's that simple. When you turn up the volume on your speakers, you're literally increasing the amplitude of the sound waves. All right, next on the list is our third fingerprint, frequency. This one tells us how many complete waves pass by a certain point every single second. For sound, frequency is everything to do with pitch. A high-frequency wave means a high-pitched sound, like a whistle. And the low-frequency wave, that means a low-pitched sound, like a deep bass drum. And our final fingerprint is wave speed. This is exactly what it sounds like. How fast is that disturbance, that energy, actually traveling through the air or whatever medium it's in? And what's so cool is how it connects to our other fingerprints with a simple but incredibly powerful equation. The speed of a wave is just its wavelength multiplied by its frequency. This is a core rule in physics, so it's a great one to remember. And there you have it, the complete anatomy of a sound wave. We cracked the case, we identified it as a longitudinal wave, and we profiled its 4 key fingerprints: wavelength, amplitude, frequency, and speed. Look, if you remember just one thing from this whole explainer, please make it this. It is the foundation for understanding everything else about sound. Say it with me. Sound waves in air are longitudinal waves.